So this problem is about momentum and impulse, and it's a problem in which a person whose mass is 75 kilograms and is falling with some velocity, 6.4 meters per second, is going to land either stiff-legged or is going to bend their knees as they're landing. And the question is, what is the average net force to that person in the different cases? And the question claims that you can avoid injury by bending your knees. So we'll find out in the question how that comes about. Of course, the difference between the two cases is going to be the amount of time it takes for that person to come to a complete halt starting with this velocity. So in the case of stiff-legged, they come to a complete halt in 2 milliseconds. In the case of bent knees, it's much longer at 100 milliseconds. So we'll find out the average force, and we'll see in which case the average force is going to be larger. Of course, to find out the average force, I think I need to calculate the impulse. Because of course the impulse is equal to the average net force multiplied by the time of action of this force. So if I know the time in both cases and I need to calculate the average force, that means I need to calculate the impulse. But I also know that the impulse, by the impulse momentum theorem, the impulse is related to the change in momentum. The impulse momentum theorem says that the impulse of external forces is equal to the change in momentum, which is the final momentum minus the initial momentum. In these two cases, the initial momentum is going to be the same, as we're going to see, and the final momentum is also going to be the same, leading to exactly the same impulse in both cases. But what's going to make a difference is the amount of time that the force is acting to get that same exact impulse. And that's going to change the value of the force. So to find out the impulse, I'm going to need to calculate the momentum. And I know the momentum is going to be mass times velocity. So let's start out calculating the momentum in both cases, before and after. So like I said before, really the time it takes to get to the complete stop does not factor into the momentum. The momentum before is mass times velocity before, and that's the same in both cases. The momentum after is mass times velocity after, and that's the same in both cases. So in both cases, I can calculate the difference in momentum. So we'll put that right in the middle. The change in momentum in both cases is equal to the momentum final minus the momentum initial, which is equal to the mass times the velocity final minus the mass of the man times the velocity initial. And the velocity is a vector, so I get to decide which direction I want to represent the positive and which direction I want to represent the negative. And maybe I'll just pick this one arbitrarily to represent the positive. So all vector quantities that are pointing up are going to be positive for me. All vector quantities that are pointing down are going to be negative. In this case, in both cases, the initial velocity is 6.4 meters per second, and this person is falling. So because they're falling, then that velocity initial is going to be minus 6.4. And the final velocity, the person comes to a halt in both cases. So in both cases, the final momentum is 0, because the final velocity is 0. And in both cases, of course, the mass of the person, I can just sub that in. So that's 75 kilograms. In both cases, the initial velocity is 6.4 meters per second down. So that's minus 6.4 meters per second. And if you work that out, you'll find that this is 480. Momentum has units of kilogram meters per second or Newton second. It doesn't matter which one you pick, because they're equal. It's the same. So that's the change in momentum. And now I can figure out for the different cases, because I have that the impulse of external forces, which is the change in momentum, which I've just calculated, is equal to, so in other words, this is the impulse of external forces, and that is equal to the force multiplied by the time. So the average force in this case is going to be equal to the impulse divided by the time. And of course, the force is going to be in the same direction as the impulse. So 480 Newton seconds divided by the 2 milliseconds, which in SI units would be 2 times 10 to the minus 3 seconds. And in the case of the bent knees, the average force is equal to the impulse by external forces divided by the change in time, and it's the same exact impulse, but now the time is 0.1 seconds, so that just adds a 0 here, so that becomes 4,800 newtons. And here, if you work this out, 480 divided 2, that's 240, divided 10 to the minus 3 makes it 10 to the 3, so that's 480, so sorry, 240 kilonewtons. And this one here is 4.8 kilonewtons. So you see right away that when you have a stiff leg, because the time is so short, the force is huge compared to when you bend your knees and you absorb that, you make the force act for a longer time. So the average force then would be smaller, 4.8 kilonewtons compared to 240 kilonewtons. So if you don't want to do any damage to your knees, I would recommend bending them. And you don't bend them, of course, before you hit the ground. As soon as you hit, you start bending, so you make the force act for a longer time. So the second part of the question, or the third part, for those keeping track, is asking about the normal force. Basically, that what we've calculated here is the average net force. What we want to break that into is we want to find the normal force, which is the force of the ground acting on the person. So if I draw a free body diagram in both cases, there's the force of gravity acting on the person, and there's the normal force of the ground responding. And these two together give me this net average force when I add them vectorially. So if I just want to find the normal force, then I would say that the net force, which I've just calculated in both cases, is equal to what I decided was positive is up. So that's the normal force minus the force due to gravity. And from that, I know then that the normal force is going to be equal to the net force plus the force of gravity. And the force of gravity, I know, is going to be equal to mass times the acceleration of gravity, which in this case is the mass 75 kilograms multiplied by the gravitational acceleration. So that's 750 minus 0.2, so minus a fifth, minus 15. 750 minus 15, that's 735 newtons. So then, if I know that this is the net force, whether in this case, the stiff-legged case, or in the bent knees case, it's 4.8 kilonewtons, then I know that in the stiff-legged case, I can calculate that the normal force is going to be equal to 240 kilonewtons plus 735 newtons. So that's equal to 240, 735 newtons. And in the case of the bent, means then the normal force is going to be equal to 4.8 kilonewton plus 735 newtons. So I know that the 7 is going to be added to the 8 right here because that's 4,800. So 800 plus 700, that's 1,500. So that's 5,535 newton. And that's that.